Slide comes from the pressure difference of the high and low side of the heat pump itself. The control of system pressures to move the slide is done by a pilot valve mounted to the valve body. The pilot valve is electrically operated by a 24-volt coil connected to the heat pump control circuit. Both coils in a heat pump have the capability of being either a condenser or an evaporator. Metering of refrigerant is a little more complicated than in a straight air conditioning circuit. One thing is certain about refrigerant metering in a heat pump. Each coil must have a metering device for use when that coil is operated as an evaporator. In many heat pump designs, this means two separate expansion valves. Only one of the valves is used at a time, however, so a check valve must be used to route the refrigerant around the other valve. Metering can be done with a combination of an expansion valve on the outdoor coil for heating and a fixed restrictor on the indoor coil for cooling. Again, a check valve is used to control flow. Fixed restriction for metering to both coils is common in some designs, but it must be done in two stages. The first stage is a fixed restrictor. The second stage is also a fixed restrictor with a check valve across it. The heating cycle requires more restriction than does the cooling cycle, so the check valve forces flow through both restrictors. The liquid line restriction then is the total of both restrictors. In cooling, one restrictor is bypassed by the check valve, leaving only the other restrictor for metering. Refrigerant metering, while more complex in a heat pump, is normally very reliable and contributes much to efficient evaporator performance. Undoubtedly, the reversing valve is the most critical component in a heat pump, but the defrost control is close in importance. An evaporator operating in a sub-freezing ambient has the same effect on moisture as an evaporator operating in an air conditioner. The heat removal causes moisture to condense out on the evaporator surface. In an air conditioner evaporator, the moisture is carried out through the condensate drain. In a heat pump, it freezes. The job of the defrost control is to establish the defrost cycles to keep the outdoor coil clear of ice. A heat pump is defrosted by reversing the heat pump cycle to put it into the cooling mode. The outdoor fan is shut off to allow maximum heat buildup in the outdoor coil. At the same time, auxiliary heat is brought on to supply indoor heat during the defrost cycle. All these operations are controlled through the defrost relay, which is cycled by the defrost control. A heat pump defrost control has two primary jobs. It must initiate a defrost cycle whenever there is enough ice on the outdoor coil to reduce heat pump performance, and it must terminate defrost after the coil is cleared. The methods used for the initiation of a defrost cycle fall into two broad categories. The first type uses a timer which initiates on a predetermined time cycle. The timer initiates defrost every 30 to 90 minutes, as long as the coil is cold enough to support freezing. If the coil is above freezing temperatures, the timer skips the defrost cycle. The second method, control of defrost based on demand, attempts to measure the actual buildup of ice on the coil. Only when the coil is blocked is there a call for defrost. There have been a number of methods tried to sense the buildup of ice on an outdoor coil in a heat pump. They have varied from optical sensors to microelectronics that measure the change in fan load as ice build up on the coil. The two most common types of demand defrost controls today are the air pressure differential control and the two-temperature defrost control. The air differential control measures the pressure differential of the airflow across the outdoor coil. This differential pressure increases as ice builds up on the coil. At a predetermined pressure differential, the switch closes and the heat pump goes into a defrost cycle. Termination of the defrost cycle is most often done with a thermostat mounted to the liquid line. The defrost cycle is terminated when this location reaches the cutout point of the thermostat, normally about 65 degrees. This method of termination is universally used in all defrost controls. Many defrost controls also have a built-in time override in case the control does not terminate on temperature. Upon termination, the defrost relay coil is de-energized and the heat pump returns to its heating mode. The outdoor portion of the heat pump looks much like a straight cooling unit. The major difference is the addition of the reversing valve, the defrost control and relay, and the metering devices. The indoor unit houses a coil along with the auxiliary heaters and the blower. The indoor coil is specially built to take the higher pressures of the heat pump. Straight cooling coils cannot be used. The auxiliary heat banks are normally sized at 100% of the heating load. In residential heat pumps, the auxiliary heat varies in size from 5 kW to about 25 kW. Heat pump thermostats are specially built to handle an increased number of control circuits. Both electromechanical and digital styles are available. All have emergency heat mode override. Some thermostats are combined with an outdoor thermostat. This type control allows auxiliary heat only when the outdoor temperature drops below the balance point of the heat pump. With improved capacity and efficiency, the balance point of high-quality heat pumps is being lowered with each new design. The heat pump brings with it a built-in efficiency that has made it a very popular heating and cooling system. Its popularity is not short-term. Energy from fossil fuels is limited, and their costs can only rise. The heat pump is ready to fill the need. It is a technology proven to be cost-effective and reliable. A key partner in this technology is the technician, the key to good performance in any installation.